Hi guys, today we're going to be starting C4.1, which is the topic of predicting chemical reactions. So looking at trends in the periodic table and what to expect from each group. So the first part of the periodic table we're going to be looking at is the noble gases. Okay, so what we're going to be able to do by the end of the lesson is recall the properties of group 0 elements, or noble gases, be able to explain the properties of these and how that depends on the outer shell of electrons, and we're going to be able to explain how the properties of group 0 elements change down the group. So first thing I'd like you to do is read these 5 statements, and I'd like you to decide whether you think they're true, they're false, or they could be improved, and then write down the corrected versions or improved versions of each of them in your books. So pause the video now, give yourself about 5 minutes to do that. Okay, here's some corrections that I got. So the electronic configuration of lithium is 2,1, not the other way around like it said in the other question. Moving around to the bottom left, many chemicals are reactive, however some chemicals are unreactive. So not every single chemical is reactive. Okay, now coming to this middle one, gas particles are far apart and are able to move freely. So they're not tightly packed and they're not just vibrating in place. They're able to move freely and they're far apart. Thinking back to C1.1 with that one. So gases are sometimes made from more than one atom, but can also be solitary atoms. So examples of some that are made from more than one atom is if we've got hydrogen, goes around as H2, so there's 2 hydrogen atoms bonded together. Same with chlorine, there's Cl2, so 2 chlorine atoms bonded together. Same with nitrogen, bromine, iodine, oxygen, lots of others. But we'll see later in this lesson that some gases can just be solitary atoms. So they're not always made from more than one atom. Okay, noble is a word with multiple uses. We can use it in chemistry also. So it's not just to do with royalty like the starter was saying. It does have other uses like we'll see in chemistry today. Okay, so your homework is to complete a worksheet on group 0. It should be attached on Show My Homework. Okay, so today we're doing about the group 0 elements, also known as the noble gases. First things first, we're going to watch a short little video about what we use them for and why it's very useful that we found them. So, quite an intense video, but we'll think about why that disaster happened and what's noble gases got to do with that. So the reason that caught on fire was that hydrogen was the gas that was inside it to keep it afloat. Now hydrogen is very light, so it is able, it's not very dense is probably a better way of putting that. So it will rise up and allow the blimp to float. But hydrogen, as you saw in the video, is very flammable. It sets on fire very easily. So let's have a think. With all of that information, why do you think that we use helium rather than hydrogen in blimps or airships today? So pause the video, give yourself a minute to think about it, and I'll give you the answer in a second. Okay, so all group 0 elements have two things in common, and helium is a group 0 element. They're unreactive and they're gases. Now these two things allowed helium to be a very useful gas to put in a blimp. So the fact that it's unreactive means that it won't set on fire. Yes, it's not flammable. So there's no way that this disaster would have happened if helium was inside the blimp. And the fact they're all gases allows it to actually fill the blimp and let it carry out its purpose. But it's not just helium that has these two properties, it's every single element in group 0. So if you copy that down into your books. Okay, so where are the group 0 and where are the noble gases? Well, it's this group here on the far right hand side of the periodic table. So we've got helium, neon, argon, krypton, xenon and radon. All of those are group 0 elements and noble gases. Okay, so pause the video here and I'd like you to try and see what trend happens in the melting points and the boiling points as you go down the group. So as you go from helium to krypton, what happens to the melting and boiling points? Okay, so as you can see, the melting and boiling points both increase as you go down the group. Okay, so they're getting less negative as you go down the group, which means they're getting harder to melt and boil. Now they still all melt and boil at very low temperatures, but it's super easy to boil helium, a little bit harder to boil krypton. So why is this? So it's simply because the smaller the atom is, the easier it is for it to keep moving around rapidly. So if you have a tiny helium atom, it's quite easy for it to whiz about. It doesn't take much energy for that. Whereas krypton needs more energy for it to be moving about. Okay? Now do copy this down because this is quite a common exam question. Asked to explain the boiling points. And it's simply because the smaller the atom is, the easier it is for it to keep moving around. So easier for it to be a gas. So it boils sooner at a lower temperature. Okay, so this is a lot of extra information on this slide that you don't really need to know. But it just gives some of the uses of our noble gases. So they're all used in lights. You might have heard of neon lights. And that's often used as a general term for all of these brightly coloured lights that you see like outside shops and stuff like that. But technically a neon light is only ever the red one. Yeah. So different noble gases will give different colours, and the reason for that is below. You don't really need to know this at all. Okay, so what I'd like you to do is draw the electron structure for helium, neon and argon. So pause the video here, give yourself a solid 10 minutes. You might need to go back and look over some notes, that's absolutely fine. Go through the answers in a second. Okay, so here's our answers. So for helium, its electronic structure is just 2. It's got 1 shell, and it's a full shell. It's got 2 electrons. Remembering our first shell can have a maximum of only 2 electrons. For neon, it's got 2 shells. The first one is full with 2 electrons in it, and the second one has 8 electrons in it. Going down to argon, we've now got 3 shells. First one has 2. Second and third one both have 8. Now, what do we notice about all of these outer shells? Write a little sentence in your book. What do you notice about the outer shells of all of these atoms? Well, they're all full outer shells. All of these outer shells have the maximum amount of electrons they can possibly have. So, this is actually the reason that all of the noble gases are unreactive. It's because they have full outer shells. So thinking back to C4.1 about bonding, if ever something tries to react and form a bond, it's usually gaining or losing or sharing electrons. Now, if it already has a full outer shell, there's no reason for it to gain or lose electrons, so it doesn't like to do it. So it'd rather just go around on its own, which makes it very unreactive. Okay, so as we just said, these elements don't react by making ions and don't make molecules because they don't like to gain or lose electrons. So we say that their electronic structures are stable because they don't like to gain or lose electrons. So this full outer shell means that they are stable. Okay, got 3 quick questions for you. So if you pause the video here and try and answer them. Okay, so our answers to question 1. They all have full outer shells. Second question, helium's outer shell can only hold 2 compared to the other 2 which can have 8 in their outer shell. Because remember, that first inner shell can only hold 2 electrons. So none of these gases, none of these atoms form ions, because they have no spare outer electrons to give away and there's no gaps in their outer shell to fill. So they don't like to gain or lose electrons, so they do not form ions. Okay, so we've got 7 questions here for you to work through. If you stop the video here, answer those questions, and that's a job very well done.